Let's now go back to the formula we were given, which is y, our ending amount, equals a, our starting amount, times 1. When we decide if we do plus or minus, the r, which is our rate or percent, to the t power. We're going to write some models and look at 4 slides in doing that. We first want to determine if it's a growth or decay. This example here says 1 year a clothing company had 1.5 million in sales. I'm going to highlight that. In later years, the sales, which is y, increased about 25% each year. They want us to write a model that represents the sales after t years, and then they want us to predict with it. So for this one, we can tell it's increasing, so we're going to use plus. So the formula is going to be 1 plus. The rate on here is the 25%. Be careful, as a percent, you have to write it as a decimal, so 0.25. They don't know the years, so we're going to put t, and our starting amount was 1.5. We do not know the ending amount, so I'm going to leave it like this. Now, we typically would simplify this to just combine the 1 and the 0.25 and write y equals 1.5 times 1.25 to the t power. Now, part B wants us to evaluate or predict what the sales will be after 8 years. So since t is time in years, I'm just going to put an 8 in there and put it in my calculator. If you type it in this order, the calculator, if you do a caret of 8, will actually do PEMDAS correctly and give us the answer, which is going to be in sales. It'll be dollars, so it'll be $8.94 million in sales. Now they want us to do the same problem, but redo it with a 10% each year. So again, remember that we started with 1.5 million in sales, and we're doing 1 plus. This time a 10% rate would be 0.10 to the t power. So our equation is going to be 1.5, 1.10 to the t. Let's actually put 8 in for the years and see how the sales differ when we change the growth rate from 25% to 10%. Hopefully you can recognize that the value should be smaller since the growth rate is quite a bit lower. The sales now are going to be at $3.22 million, which is quite a bit lower versus if we had a 25% growth rate. Let's look at a second example. This one's going to be decay, and if you listen to as I read it, you'll see why. You buy a computer for $1,500, so that's our starting amount. The value y in dollars of the computer decreases by 40% each year. So write a decay model. Again, the model format would be beginning amount 1 minus the rate to the t. So we are starting with $1,500 computer. The rate is 40%, and we don't know the time. Simplify this formula would be y equals 1,500, and I'm going to do 1 minus 0.4, which is 0.60 to the t power. So that's the equation that I would type. They want us to use the model to predict the value of the computer after 3 years. So I'm just going to put a 3 in for t and simplify with a calculator and see what we get. Again, if you put this in the calculator just as you see it, it will do PEMDAS correctly. It will do the exponents first and then multiply. This computer will be worth $324. Okay, the second part of this, they're changing it up a bit. This time we have a new computer that costs $1,200, so it's a little bit less, but its actual rate of decay is also a little bit less. So let's just see what the value of this computer would be after 3 years. So our ending amount, we don't know. The starting is $1,200. 1 minus the 0.35%. And let's just go ahead and put the 3 years in there right now. I'll show you the simplification of this. 1 minus 0.35 is 0.65 to the third power. So in your calculator, I'm going to type this. I'm going to say times 0.65 to the caret of 3. And when you do that, you're going to get $329.55. So after 3 years, the cheaper computer is actually worth just a few more dollars because it depreciates at a slower rate.